Okay, so picture this. You're in your kitchen. There's a 12-month-old in a high chair. They've got mashed carrots everywhere, and they want out. So they look at you, they put their little arms up, and they go, ah, ah.
The classic.
Yes.
The universal, pick me up now.
Exactly. And you know what it means. You pick them up, but, I mean, linguistically. It's pretty basic, right? It's just a signal.
It's a signal and response. You wouldn't call it a conversation.
Not at all. But then fast forward to 6 months, that same kid is saying, mommy out.
Okay, a bit more specific.
Right. And then a year after that, so now they're 2, they're yelling, Mom, I want to get out of this chair right now.
Yeah, the transformation is just, it's staggering when you lay it out like that.
It honestly feels like magic. How do we go from grunts to, complex grammar and demands in such a short amount of time?
That question, that exact question, has basically split the scientific community in half for, 50, 60 years?
And that's exactly what we're digging into today. We are exploring this huge debate in the science of language. Is talking an innate instinct that's just hardwired into our DNA?
Like a spider spinning a web.
Right. Or is it something we build brick by brick through these incredible feats of learning?
To guide us, we're looking at this really seminal chapter by Anne Fernald and Virginia Marchman, and they're basically challenging the old guard.
The old way of thinking.
Exactly. With new evidence that suggests babies aren't born with a language manual, they're actually, brilliant little statisticians.
Statisticians? I mean, that sounds incredibly dry for a toddler.
It sounds dry, but the implications are pretty wild. It suggests that while you think your baby is just staring at the wall, they're actually running complex data analysis on every sound you make.
Okay, let's unpack that. Because when I took Psych 101, I definitely learned about the old guard. The heavy hitters like Noam Chomsky, Steven Pinker.
Right.
And the general idea was that language is just, it's too complicated to learn from scratch.
Exactly. That's the nativist view. So back in the 1960s, Chomsky proposed this idea. He called it the language acquisition device.
Which sounds like a kitchen appliance.
It does. But the core argument behind it was this concept called the poverty of the stimulus.
Which is just a fancy way of saying adults are terrible speakers, right?
Essentially, yes. If you actually listen to how we talk, it's a mess. It's chaotic. We say, and we start sentences and don't finish them.
We make mistakes.
All the time. So Chomsky's argument was, how could a child possibly learn the perfect, complex rules of grammar from such messy, chaotic input?
It's like trying to learn chess by watching 2 people who keep knocking the pieces over.
Perfect analogy. So his conclusion was, you can't learn it from that mess, so the rules must already be inside you.
So the baby comes preloaded with the software.
Precisely. Steven Pinker really popularized this. He called language an instinct. His analogy was great. A spider spins a web because it has a spider brain.
Not because it went to web spinning school.
Exactly. And humans talk because we have a language mental organ. It's not learned, it's just triggered.
It's a really compelling idea.
Yeah.
I mean, it explains why every healthy kid just learns to talk. You don't teach them.
You don't.
But our source material today says the pendulum is swinging the other way.
It's shifting in a big way. This is the constructivist view, and the argument is that language is, constructed from experience, and the key isn't a grammar switch. It's something called probabilistic constraints.
Probabilistic constraints. That sounds a lot more technical than instinct. What does that actually mean?
It just means we don't rely on one single rule book. We're using multiple sources of info all at once, context, what we see, tone of voice to guess the meaning.
We're playing the odds.
We're constantly betting on what we think is being said.
There's a really cool study they mentioned, the one with the apples and the towels, the Tannenhouse eye tracking study. I love this because you can see the brain working in real time.
Oh, this is a classic. So imagine you're in the experiment. I put 2 things in front of you, an apple sitting on a towel and an empty box.
Okay, apple on a towel. Empty box. Got it.
Now I say, put the apple on the towel into the box.
Put the apple on the towel into the box. Okay, it's a little clunky. My first thought when I hear put the apple on the towel is you want me to move an apple onto a towel.
Exactly. You think on the towel is the destination.
Well, then you say into the box. And I sort of backtrack in my head and realize, oh, you meant the apple that's already on the towel.
Right. That confusion is called the garden path effect. You went down the wrong path. Now, if the nativist view is right, you should get confused by that every single time.
Because the grammar itself is ambiguous.
It is until the very end, but that's not what happened. They tracked people's eyes. And with just one apple, people did get confused. They'd look at the empty towel first.
But There's a twist.
Here's the twist. If they put two apples in front of the person...
Let me guess. One on a towel, one on something else. A napkin.
Exactly. If there were two apples, the confusion just vanished. People didn't even hesitate. Their eyes went straight to the apple on the towel.
Why? What changed?
They used the visual context. Their brain immediately realized, oh, there are two apples, so he needs to specify which one. So when they heard on the towel, they instantly knew it was a description, not a destination.
So we're not just processing grammar in a little box in our heads. We're using what we see to figure out what we hear, like on the fly.
Instantly. We're using probability and context to solve the puzzle, and the argument is that babies are doing this from day one.
Well, let's talk about day one, because one of the most surprising things in this is just how much work a baby is doing before they ever say a single word.
It's massive. You know, back in 1970, a researcher named Bernard Friedlander actually complained that nobody was studying how babies listen. Everyone was just obsessed with what babies said.
They output.
Yeah, they were ignoring the input. But soon after, we found out babies are basically super listeners.
How do we even know that?
Well, in 1971, Imus and his team proved infants could hear the difference between ba and pa just by measuring how they sucked on a pacifier.
Wait, a pacifier? How does that work?
It's actually really clever. Babies suck harder when they're interested, so they'd play ba 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 over and over until the baby got bored and slowed down.
Okay.
Then they'd switch the sound to pa, and immediately the sucking rate would shoot up. The baby noticed the difference.
That's incredible. But here's the part that gets me. We think we get better at everything as we get older, but this research shows babies are actually better listeners than adults.
Yes, this is perceptual narrowing. It's this idea that to become an expert, you actually have to stop paying attention to everything.
Right, and the best example is the Hindi sound study.
By Worker and T's, yeah. So in Hindi, there are two different T sounds. To an English speaker's ear, like mine, they sound identical. I literally can't tell them apart.
Me either.
But here's the kicker. 6-month-old babies from English-speaking homes, they can hear the difference perfectly.
So they're universal listeners. They start out able to hear every sound in every language.
They do. But, and this is the crazy part, by the time they're 10 or 12 months old, they lose that ability. They stop hearing the Hindi distinction.
Which sounds like a bad thing. Why is losing an ability a good thing?
It's all about efficiency. It's called neural commitment. The brain basically says, okay, I live in an English-speaking house. This particular sound difference doesn't matter here, so I'm going to stop wasting energy on it. It tunes itself.
It specializes.
You have to specialize to get fluent. You prune away the data that isn't relevant to your environment.
Okay, so once they've seen into the right sounds, they have an even bigger problem.
The segmentation problem, yeah.
The where does one word end and the next begin problem.
Exactly. I mean, if you've ever listened to a language you don't speak, it just sounds like one long, continuous stream of sound.
Blah, 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 blah.
That is exactly what a baby hears. In real speech, we don't actually pause between dot words like this. So how does a baby know, look at the pretty baby isn't one giant word?
This brings us to that Pabiku study, and I feel like this is the smoking gun for the whole statistician theory.
Oh, I love this study. Safran and her colleagues in '96. They wanted to see if babies could find patterns in just, well, pure noise. So they played a stream of nonsense syllables for them.
What did it sound like?
It was a flat, robotic voice. Pabiku galacta pabiku, on and on and on.
Just total gibberish.
Seemingly. But hidden inside were patterns, 3-syllable words. So pabiku always appeared together, and golatu always appeared together.
But there were no pauses between them.
No pauses at all. But statistically, if you heard pa, it was almost always followed by ba. But after ku, the end of a word, the next sound could be anything.
So the syllables inside Pabiku had a high transitional probability. They stuck together.
Precisely. And after just a few minutes of listening, the babies got it. They recognized pabiku as a word.
How do they show that?
When the researchers played pabiku by itself, the babies were bored. But if they played a mixed-up non-word, like kugala, which crossed a word boundary, the babies perked up. They noticed the pattern was broken.
That is just wild. So they're literally calculating statistics on syllables before they've even had their first birthday.
It shows you don't need a pre-programmed grammar rule to find words. You just need a powerful learning brain that's really good at tracking patterns.
Okay, so they can find the words in the stream. That's step one. They know Pabiku is a thing, but how do they figure out what Pabiku means?
Ah, yes, the mystery of meaning. Philosophers have been pulling their hair out over this for centuries.
We have to talk about the GABA guy problem.
The classic GABA guy from the philosopher Quine.
So for anyone listening, the puzzle is this.
Hmm.
You're in a foreign land, you don't know the language. A local guide points at a rabbit that hops by and says, GABA guy.
So you think, okay, GABA guy means rabbit.
Of course. What else could it mean?
Well, logically, it could mean food. It could mean furry thing. It could mean look at that, or hopping, or whitetail.
Or dinner. How do you know?
You don't. That's the puzzle.
Right.
Just from the input, the point, and the word, the meaning is. It's wide open.
So how did the old theory explain how kids solve this? Because they obviously do.
The old theory proposed these hardwired rules or constraints, like the whole object assumption, a rule in the brain that says, if someone points, assume they're naming the whole thing, not its parts.
Which makes sense. If I point at a dog and say dog, my kid doesn't think I mean tail.
It's a nice, clean rule, but the new research says we don't need a rigid rule for this. We have something way more powerful, social cognition.
Theory of mind.
Exactly. Human children are obsessed with what other people are thinking. They track intentions. They don't just look at the rabbit. They look at the person looking at the rabbit.
There's that great example with the mom and the fruit tart.
Right. So a mom brings out a tart, she trips, it splats on the floor, and in frustration she yells, rhubarb! Now, if a kid was just a simple robot, they'd see the tart, hear the word, and conclude the tart's name is rhubarb.
Or that rhubarb means oops.
Right. But the child doesn't do that. The child looks at the mom's face. They see she's surprised, annoyed. They realize she didn't intend to label the object. She was just reacting.
So they basically just throw that data point out. Oh, she's not naming something. She's just yelling.
They're using social cues to filter the linguistic data. They're reading her mind.
So we're not just little computers calculating sounds.
Right.
We're social detectives.
And that's crucial. Language is learned in a social context. We use joint attention, looking where mom is looking, to solve the GABA guy problem.
Which explains why you can't just put a baby in front of a TV and have them learn a language.
People have tried. It doesn't work very well. The TV doesn't look back. The social feedback loop is broken.
Okay, so we have sound statistics, we have social detective work. Now let's talk about when it all comes together. The vocabulary explosion.
Burst, yeah.
Happens around 18 months, right? They're learning words so slowly, and then suddenly, bam, they're learning like 10 words a day.
The old view was that this was some biological mechanism just turning on. But computer models, connectionist models, they show this burst happens naturally.
Without a special switch.
How? It's a snowball effect. Once you have a certain number of words in your network, it gets way easier to add new ones. You start recognizing the patterns faster.
And what about what they learn? I've always heard that kids learn nouns first. Ball, dog, milk.
That's true for English-speaking kids. And for a while, people thought this was a universal noun bias, that the human brain just prefers concrete objects.
But that's not the whole story.
No. If you look at kids learning, say, Mandarin or Korean, they often learn verbs much earlier.
Why the difference?
It's all about the input. In English, we tend to put the noun at the end of the sentence where it gets the stress. Look at the ball. But in Korean, the verb often comes at the end. The sentence structure itself highlights the action, so the baby tunes into whatever is most prominent in their language.
So again, it's not some innate noun instinct.
Yeah.
It's just the baby crunching the numbers on what it hears most often.
They adapt to the statistics of their environment.
Which brings us to the final piece of the puzzle. Grammar. The nativists always said grammar and vocabulary were totally separate.
Right, like a dictionary and a rule book that don't talk to each other.
But the evidence says that's not true.
Not at all. They're tightly linked. Bates and Goodman found that the single best predictor of a child's grammatical complexity is just their vocabulary size.
So you can't build sentences until you have enough bricks.
Pretty much. As you learn more words, you start to see the patterns of how they fit together.
But there's another factor here, and this is the one I find so fascinating. It's about speed.
Yes, the looking while listening study. This is Anne Fernald's work, and it's so important.
So they measured how fast kids process words.
Exactly. So you take a 15-month-old, you say, "Where's the baby?" And they wait until you finish the entire word baby before they even start to look.
They're buffering.
Totally. But a 24-month-old, you say bay, and their eyes are already moving to the picture of the baby.
They're predicting.
They're processing incrementally. And this is huge, because if you're slow, You're always one word behind in a conversation.
You can't keep up.
You can't. But as you get faster at just recognizing the words, you free up brain space. You free up cognitive resources to notice other things, like, oh, the word the usually comes before dog, and the word barked comes after it.
And that's how you learn grammar.
That's the theory. Processing efficiency is what lets you spot the patterns of syntax. You don't need a magic grammar module. You just need a really fast processor.
That is such a cool way of looking at it. It actually makes it more impressive, not less. It means every toddler is doing this high-speed data analysis all day long.
It really reframes the whole nature-nurture debate. We aren't blank slates, but we aren't born with the answers either. We're born with incredible tools to find the answers in the data around us.
So we've moved from the idea of a baby having a pre-programmed spiderweb instinct to a baby being a powerful statistician and a social detective.
That's a perfect summary. Language isn't this isolated organ. It's built by integrating sound, society, sight, and speed. It's a masterpiece of construction.
It really makes you look at a baby differently. You realize they aren't just staring off into space. They're judging your intentions and calculating your transitional probabilities.
They're working harder than any of us.
So before we wrap up, I want to pose a final question based on all this. We've established that babies learn from the statistics of the input, what they hear.
Right. The input is the fuel.
Well, what happens when that input changes? I mean, we live in a world of digital assistants now. Kids are hearing Alexa, Siri, AI voices more and more.
That is a very provocative thought.
If babies learn from the messy, probabilistic ums and ahs of human speech, what happens when a big part of their input becomes perfectly synthetic, when the statistics of their world become artificial?
It's a fascinating real-time experiment we're all running. If the learning mechanism is fine-tuned to the statistical properties of human speech, and we change those properties,
we might change how the next generation learns to talk.
Yeah.
Will they get better at processing clean speech, but worse at messy human communication?
Or maybe they'll just get really, really good at talking to machines. It's hard to say. But that little statistician in their brain will be working with whatever data it gets.
Something to think about the next time you ask your smart speaker to play Baby Shark for the 50th time.
Indeed.
That's it for this deep dive. Listen to the statistics in your own conversations today. You might be surprised at what you hear. Thanks for listening.